Welcome back, compadres. I'm Brandon Tolbert, and today we're talking petroleum engineering. Oil wells, they don't only produce oil, they produce gas also. So you need to be able to forecast gas production in order to determine the economic limit, or EUR, of the well. The problem is you can't just forecast off the entire gas production. That's a no-no, man. That's not accurate, because the way a oil well produces above the bubble point is different than the way it produces below the bubble point. So you have two distinct regions, and you need to separate them independently and forecast them independently. So today, I'm going to show you a methodology that can help you do that using a log-log interpretation to forecast GORs in those two distinct regions. Also, from this analysis, we'll be able to pull values that will help us determine drainage area. So guys, if you're not excited, I don't know what will get you excited, so let's go ahead and get started. So today I'm going to demonstrate how to determine the cumulative production up to the bubble point, initial GOR, and develop forecasting equations for GOR for the undersaturated and saturated region. So why do we want to determine the cumulative production up to the bubble point and initial GOR? Because it helps us to determine drainage area of a well, which in turn helps us determine well spacing, how far we want to put these wells apart in a given area. So why do we want to forecast the GOR equations? Because they help us determine the economic limit of a well, or EUR of a well. And so when you forecast GOR, what are we doing with this analysis? Why is it important? Because we have two distinct regions. We have a region where we produce above the bubble point and a region where we produce below the bubble point. So this analysis helps us define those two regions. That way we don't forecast the entire gas production data of a well and end up with a bad analysis, because it's not indicative of the state of the reservoir. So what's shown here, this is the bread and butter of analysis. We're going to use straight lines as shown here, going through two separate regions. This region over here on the left is when the reservoir is above the bubble point, or in the undersaturated condition. This condition on the right, this line's going through the data where the reservoir is below the reservoir pressure, or in the saturated region. So some key points I want you to think about as we go through this is log-log line interpretation. That's really the fundamental thing I want you to learn from this analysis. And we're going to do all this in 4 steps. So it should be easy and straightforward, or I try to make it easy and straightforward. So before we go into our analysis, we need to understand how a reservoir behaves, especially a reservoir that we're trying to analyze, that is one that is initially producing above the bubble point. So this is a graph from McCain's Petroleum Engineering Reservoir Fluids, and as you can see, we got gas-oil ratio plotted and pressure plotted as a function of time. So this graph identifies two distinct regions: the undersaturated region, where the reservoir is above the bubble point pressure, and then the saturated region, where the reservoir is producing below the bubble point pressure. So you can see the gas-oil ratio trend is it's constant above the bubble point because the gas stays in solution. When it crosses the bubble point, the GOR just increases real fast. That's because gas comes out of solution, and gas produces at a higher rate than oil because of relative permeability and all those reservoir dynamics. But the fact is, you have two distinct regions, and so we're going to fit these two regions with two functions. The same with pressure. The pressure declines in the undersaturated region at a fast rate, and then once it hits the bubble point pressure, gas evolves in the reservoir, and the reservoir pressure declines at a slower rate because gas is more compressible. But you can see here, this is the fundamental assumption of our analysis, is we're starting with a reservoir above the bubble point pressure, and we have two regions, undersaturated and saturated region, which we have to develop functions for. And we'll show you how to do that in the next slide, and how to identify these two regions. So this is the theory behind our analysis. The two fundamental equations we're going to use our fit equation, a power function. Okay, this is the parent function. It's this exact same equation with x as the cumulative oil production and y as the cumulative gas production. You take the derivative of this, you get GOR. So this is what we're forecasting right here. that will help us with our economics later on in a different video. And so if you take the log of both sides, or the natural log of both sides, you can rearrange this and form a straight line. This is your straight line on a log-log plot, where m is your slope, and this value right here, the natural log of the, what I'm going to call the intercept. So this is the coefficient right here. It's the intercept of this interpretation. It's going to be b in our y equals mx plus b, which everybody's seen before. So the key point is, when this m, or slope, is equal to 1, it implies a constant GOR. It also means that on a log-log plot, our intercept is equal to our initial solution gas-oil ratio, which we use to determine drainage area. And so how do we apply this to the data? Well, generally what you're going to do is you're going to start with, you're going to assume a log-log straight line with m equal to 1, a constant GOR line. And so you're going to set this through the early time data. You're going to eyeball this. And the intercept you come up with right here is going to be your initial producing gas-oil ratio, because you can see here the intercept on a log-log plot is at a value of 1. So your x is equal to 1, your y is some value, so y over 1, well, that's going to be your slope. So then you're going to fit this data the best you can with this constant GOR line, and then you're going to have another set of data that's not going to fit it. You got to fit it with another function. So you're going to use this power function, and you're going to regress off of the rest of the data below the bubble point. And the intersection of these two lines is equal to the cumulative production at the bubble point. So really there's three key pieces of information you're getting from this plot. The initial produced gas-oil ratio right here, your cumulative production up to the bubble point, which is at this deflection point, and then your GOR forecasting equation for after the well falls below the bubble point, which you use in your economic analysis. So these two regions identify the undersaturated region and the saturated region. And so you distinguish those two, and you can forecast your gas production a lot better. It's a lot better way to do it. So you identify that transition and you move on. And so the 4 steps we're going to apply in this analysis is: step 1, I want you to plot the cumulative production versus the gas cumulative production on a log-log plot. That's the first step. The second step is to fit the data above the bubble point with a log-log straight line with a slope equal to 1. And so this is your undersaturated region, and you can determine the initial GOR from this fit as shown in the previous slide. Step 3 is to regress off the saturated reservoir data and determine your GOR function for below the bubble point. And then step 4 is to determine the cumulative production up to the bubble point by determining the intersection of the two lines. And that can be done mathematically, and I'll show you that in the next slide. And so that's the steps for forecasting GOR. It's just 4 steps. Pretty simple. And so this is the math for determining the log-log intersection of 2 log-log straight lines. And I programmed this in VBA, but here's the math behind it. You have your saturated reservoir region, which is fit by this power function, and it's got a slope equal to 1. You have line 2, your undersaturated reservoir condition, which is fit by another power function. And so you set those two equal to each other, and then you can do the math, and you end up with, you solve for the cumulative oil production in terms of the cumulative oil production, and you get this equation. You substitute M1, or the slope of the first line, equal to 1, and you end up with the cumulative production at the bubble point. So that's how you do it, guys. Pause the video, work through the math, understand this. This is a big step. And guys, we will proceed with it. We will proceed with the analysis right now. Let's start the analysis in Excel. So I'm using production data from the horizontal well in New Mexico that we used in the first video. And so what I've done is I pulled in the cumulative production up to the the cumulative oil production and the cumulative gas production. And I've calculated a GOR right here. It's just the ratio of the two. And I'm using units. I converted it to units of standard cubic feet per stock tank barrel. So before we get into this log-log interpretation, straight line interpretation, I want you to look at the GOR of this well. So if you plot the GOR versus time, you can see this is the graph. What can you tell from this? You really can't tell much. It's hard to determine where the constant GOR is. It could be this region, it could be this region, maybe this region. I mean, this is difficult to tell. And so you can see, you definitely can't tell the cumulative production up to the bubble point. I'll tell you that much. And so this is why doing it this way, if you're going to forecast GOR with this equation, you shouldn't do it, because you can't identify the region, the saturated region and the undersaturated region. And so you needed to decipher those two in order to do an accurate forecasting of GOR. And that's the motivation behind doing it with a log-log straight line interpretation. So here on this cumulative gas production versus cumulative oil production graph, I plotted this data. And so we're going to zoom in and try to find a deflection point. And so I'm going to go with 5,000. And then I'm going to go over here and go 10,000. So guys, this is a lot cleaner. Look at this data. You can actually see the deflection point. It looks like it curves right here. You have a straight line here and then a straight line up there. So the first part in our analysis is to fit the first or the undersaturated region with a straight line, assuming a constant GOR. So here's my key. Anything highlighted in purple is going to represent the undersaturated region. Anything in blue is going to be the saturated region. So step one, let's look at this. So we assume a constant GOR, so our slope will be equal to 1. And then now we know from our intercept of this line right here, with the slope equal to 1, it's going to be represent the initial producing GOR. So if we go to our data, I'm going to just say it's equal to 640 standard cubic feet per stock tank barrel. And notice here I'm using different units, so divide that by 1,000, and we get that result. And so now I want to plot this line on this graph and then eyeball a best fit. So this is our equation we're using, as we showed in slide 3. So let's do that. It's going to be our intersection point, just right here, times our cumulative production, which I've just chosen a point that spans this graph's region. And I want to lock these in, because I'm going to use them to determine the second point of our straight line to the power of our slope. So there we have it. And so I'm going to drag this down, and you can see here's our straight line. Now we're going to fit it to this data, and so you can see our initial guess, it's a little bit low. So I've already done this analysis. So the best fit that I came up with was when the GOR equals 1,400 standard cubic feet per stock tank barrel. And so you can see the fit up here. It's a good fit. It fits our early time data. So this represents our GOR forecasting function in the undersaturated region. So now remember the two key pieces of information we can get from this, or the one key information we can get from this is initial producing GOR. And so I'm just going to determine that, multiply that by 1,000, and then that's what we're going to use our initial producing GOR right there. So now we need to look at fitting this region, the saturated region. So I'm just going to regress off these parameters. So I'm going to say the deflection point occurs at this point right here. And so I want to look at my data and find that point. I've already highlighted it. So right here is where I'm going to start regressing off. I'm going to regress off this data and later. So all the way down to here. And so recall that for a straight line log-log plot, our straight line equation is right here. And so this is analogous to y equals mx plus b. So our slope is m, and then our intercept is going to be the natural log of the intersection. And so that's what we're going to show here, how to regress off that with a Excel function. So this is our slope. It's just our y's, or our change in y's over our change in x's. So let's show how to do that in Excel. So we use our regression function in Excel. It's just going to be the slope. But since our slope has natural logs in it, we're going to use a natural log of our y's and x's. So our y's is going to be right here. So we're regressing off of that. I'm going to lock these in, and then I'm going to do the natural log of our x's. And I'm going to lock those in by pressing F4. And that's our slope. That's our m value in this equation. So now I want to go ahead and determine the intercept right here. So we just do the same thing we just did, except we change this from slope to intercept. Intercept right there. I like it. Okay, so that's our intercept. And so what we have here, if we're going to use this equation, we're going to have to raise this to or take the exponential of it and raise it to this power right here, and we get our intersection right there. So exponent of that, bang, bang. Okay, so now we can put this result and plot it on here. So let's use the same equation. So I'm going to drag this down. And so all I did was, well, let's don't drag that down. Let's rewrite the equation. So our intercept is right here times, and I'm going to freeze this again, times our cumulative oil production raised to the m subscript 2. I'm going to lock that in. So that's the result we get. And so, wow, look at that. Okay, so we regressed off of this late time data in our saturated region, and now look at that. We have our straight line interpretation. So our bubble point occurs at the intersection of these two lines. And so how do I determine that? Well, I wrote a VBA function for that. And so I'm going to just show you what it looks like. See here, here's our log-log intersection. It's the math we did in the slide presentation. It's a real simple function. Right here, it takes our two slopes of our lines and our intercepts. So I'm going to show you how to use that. So the cumulative production up to the bubble point is going to be equal to our log-log intersection. And so I'm going to put in the values, M1 right here, our intercept, M2 right here, and then our intercept. And bang, that's our cumulative production up to the bubble point. Check it out, man. So look at what we found. We found these 2 points, and we can go put these in our analysis of our drainage area. Last piece of information we need is the equation for the GOR in our saturated region. So this is basically this equation right here. We substitute our slope and then our intersection point in the saturated region, and so this would be M subscript 2 and also our intersection, and then we end up with our GR equation. This is our forecasting equation. So we can use this to help us determine our EURs and our economic limit. So guys, the whole purpose of this analysis was to get 3 pieces of information: the initial producing GOR, the cumulative production up to the bubble point, which you can substitute into what we did in video 1 to determine drainage area, and then our forecasting equation right here. So this is our 3rd piece of information. So guys, I hope you saw the benefit in doing it this way. And like I said, not every well is going to fit this way. It's only going to be wells that started producing above the bubble point, and hopefully you have clean data too. That can be an issue. But guys, you can see how we were able to do an interpretation using real production data from a horizontal well to do this analysis. So guys, I hope you like this. There we have it, guys. We use the linear log-log interpretation in order to forecast GORs of the well in two distinct regions, saturated region and the undersaturated region, or below the bubble point and above the bubble point. And also, we were able to get information from this interpretation to help us determine drainage area, such as cumulative production up to the bubble point and the initial producing GOR. So guys, this interpretation is not for every well, and it won't fit every well, but I like it because it fits the petroleum engineering fundamentals. It's something that I can understand, that you can understand, and it just makes sense, and that's why I like it. So guys, I hope you enjoyed the video, and as always, subscribe, and I'll see you next time. Adios.